These are the answers to the AP Chemistry packet on topics 8.1 to 8.3. This is MCQ Practice, which means these are multiple choice questions for you to practice so you can prepare for the AP Chemistry exam. In the video description area, there is a link to the packet that accompanies this video. Now let's take a look at our first multiple choice question. In question 1, it says, it is observed that the pH of pure water at a temperature of 37 degrees Celsius is equal to 6.81. Which of the following correctly identifies the pOH of pure water at 37 degrees Celsius and the value of Kw at 37 degrees Celsius? So this question falls under topic 8.1, Introduction to Acids and Bases. And on this slide, I've highlighted some important information that is relevant to answering question 1. Water autoionizes with an equilibrium constant Kw. Kw is equal to the concentration of the hydronium ion, H3O+, times the concentration of the hydroxide ion, OH-, and that value of Kw is 1.0 times 10 to the negative 14 at a temperature of 25 degrees Celsius. In pure water, the value of pH is equal to the value of pOH. Pure water is called a neutral solution. And then finally, the value of Kw is temperature dependent, so the pH of pure, neutral water will deviate from 7.0 at temperatures other than 25 degrees Celsius. So that is the situation that is occurring in question 1. We are at a temperature that is not 25 degrees Celsius. And then I will show you on this slide, you can see a portion of the AP Chemistry equations and constant sheet. So those equations that I mentioned are featured on the AP Chemistry equations and constant sheet. Now back to question number 1. Again, we know that we are not at a temperature of 25 degrees Celsius. So therefore, since the temperature is not 25 degrees Celsius, the value of Kw is not equal to 1.0 times 10 to the negative 14. That means that we can eliminate choice A and choice C, and so we're looking for a value of Kw that is something other than 1.0 times 10 to the negative 14. Now on this slide, this was taken from an earlier video in which I was talking about topic 8.1, and as you can see, pure water is always neutral at any temperature. The value of pH is equal to the value of pOH no matter what the temperature is for pure water. And since pure water involves pH is equal to pOH, and then in this particular question they say that the pH of pure water at this temperature is 6.81, now we know that the value of pOH must also be equal to 6.81. So the correct answer to question 1 is choice B. On this slide, you can see information about how you would calculate the concentration of the hydronium ion or the hydroxide ion if you know the pH or the pOH. So what I'm highlighting on this slide is that if you know the pH, then the concentration of the hydronium ion is 10 to the minus whatever that pH value is. So in this particular question, if we do the math of 10 to the minus 6.81, we get a value of 1.55 times 10 to the negative 7 moles per liter. Now that is not only the concentration of the hydronium ion, but that is also the concentration of the hydroxide ion in a sample of pure water, in which pH equals pOH. I'm just showing you at the bottom of this slide that if we take 1.55 times 10 to the negative 7 and we square that number, then we will get the value of Kw at this particular temperature. And so it does work out to be 2.4 times 10 to the negative 14. Okay, now that you know that the answer to question 1 is choice B, let's take a look at question 2. Question 2 says the following. At 25 degrees Celsius, enough distilled water is added to a 100.0 milliliter sample of nitric acid, HNO3, with a pH of 4.50, so that the final pH of the diluted solution is 5.20. The volume of distilled water added to the original solution is closest to, and then we can see 4 numerical choices. So I'll give you a diagram to help you figure out what exactly is going on in this experiment. So we begin with a sample of nitric acid, HNO3. The volume is 100.0 milliliters and the pH is 4.50. Then a certain amount of distilled water is added, but we don't know exactly how much. Therefore, we don't know the final volume of this diluted solution. But we do know that the pH of the diluted solution is 5.20. And so the fact that it's nitric acid is important. This does fall under topic 8.2, which is pH and pOH of strong acids and bases. So the reason why knowing that this is nitric acid is helpful, as you can see on this slide, there are 6 strong acids that you should know for the AP chemistry exam. HCl, which is hydrochloric acid, HBr, hydrobromic acid, HI, hydroiodic acid, and so forth. And so one of those examples is HNO3, nitric acid. The fact that it's a strong acid means it is 100% or completely ionized in aqueous solution. So if we know the concentration of this strong acid, then that is the same as the concentration of the hydronium ion in aqueous solution. We will see later on in this video that when we get to topic 8.3, which is weak acids and bases, it's a more complicated process of using the Ka and the concentration of the acid to determine the concentration of the hydronium ion. But in this example, it is a strong acid. So the concentration of the hydronium ion is equal to the concentration of this strong acid itself. Now, something that was mentioned in question 1 is that if you know the pH of the solution, then you can calculate the value for the concentration of the hydronium ion by doing 10 to the minus whatever that pH value is. Let's go ahead and take care of that calculation. 10 to the minus pH. So before water is added in this experiment, that would be 10 to the minus 4.50. So when we do that calculation, the initial concentration of the hydronium ion is 3.16 times 10 to the negative 5 moles per liter. But then after the water is added, we should have a lower concentration of the hydronium ion when the pH is 5.20. So 10 to the minus 5.20 gives us a value of 6.31 times 10 to the negative 6 moles per liter. So you can see that as the pH goes up, the concentration of the hydronium ion in the solution goes down. Now, what is it that we're trying to find? Well, we're trying to find the volume of distilled water that was added to the original solution. So we know the initial concentration of hydronium. We know the final concentration of the hydronium ion. We know initially the volume was 100 milliliters. So all we need to know is what's the final volume of the diluted solution. So I will call your attention to something that I had mentioned back in Unit 3. This is the dilution equation. Molarity times volume of the concentrated solution is equal to molarity times volume of the diluted solution. And you can see on this slide that the volume amounts do not have to be in units of liters. They could also be in milliliters as long as the units of volume are the same on both sides of the equation. So the only thing that we don't know is the volume of the diluted solution. So we have the initial molarity of the concentrated solution, which is 3.16 times 10 to the negative 5 moles per liter, and the initial volume before the water was added is 100 milliliters. Now, the new concentration after the solution has been diluted is 6.31 times 10 to the negative 6 moles per liter. And the only thing that we don't know is the volume, the final volume of the diluted solution. So I'm going to go ahead and solve for V final, and that is equal to the following calculation: 3.16 times 10 to the negative 5 times 100 divided by 6.31 times 10 to the negative 6. So if we do this math, we're going to figure out the volume of the diluted solution in units of milliliters. And so when you do this math, we get approximately 500 milliliters. Now, it's very tempting to choose choice D for this question, but if you read carefully, it says the volume of distilled water added to the original solution. That's what we're looking for. So we are not calculating the volume of the final solution in our answer. We're looking for the difference. So if we began with 100 milliliters and we added water and now we have 500 milliliters total volume, then you can see that that means that 400 milliliters of water is added. So the correct answer to question 2 is not choice D, but rather choice C, the volume of water added to change the pH in this experiment. All right, well, hopefully that makes sense. And now let's take a look at question 3. In question 3, it says a student dissolves 2.0 grams of solid sodium hydroxide in distilled water so that the total volume of the solution is 2.0 times 10 to the third milliliters. The pH of the final solution at 25 degrees Celsius is closest to, and then we see 4 numerical choices. So question 3 falls under topic 8.2, pH and pOH of strong acids and bases. So we have sodium hydroxide in this example. When dissolved in solution, strong bases, for example, group 1 and group 2 hydroxides, completely dissociate to produce hydroxide ions. So on the periodic table, since sodium is located in group 1, sodium hydroxide is an example of a group 1 hydroxide. The concentration of the hydroxide ion in a strong base solution is equal to the initial concentration of a group 1 hydroxide such as NaOH. And the pOH and the pH of the strong base solution is easily calculated. So let's start by converting the grams of sodium hydroxide into moles. So on the periodic table, we can find the atomic masses of sodium, oxygen, and hydrogen, and we can use those values to determine that the molar mass of sodium hydroxide is equal to 40 grams per mole. Now, we have 2 grams of sodium hydroxide, so let's convert from grams into moles. So starting with 2 grams of sodium hydroxide times 1 mole of sodium hydroxide for every 40 grams, that gives us a value of 2 divided by 40, 0.050 moles of sodium hydroxide. So this is not the concentration of sodium hydroxide, this is the number of moles. Now we can take the volume, which is 2.0 times 10 to the third milliliters, and convert that into liters, because the concentration should be in units of moles per liter. So 2.0 times 10 to the third milliliters times, there's 1 liter for every 1,000 milliliters, and that gives us 2 times 10 to the third divided by 1,000. So we have 2.0 liters of solution. Putting these two quantities together, now we can figure out the concentration of the sodium hydroxide. Remember, this is a group 1 hydroxide. The concentration of the sodium hydroxide is the same as the concentration of the hydroxide ions in this solution. So moles per liter, that means moles divided by liters. 0.050 moles of sodium hydroxide divided by 2.0 liters gives us 0.025 moles per liter. And that is not only the concentration of the sodium hydroxide, that is also the concentration of the hydroxide ion. So all we have to do now is calculate the pOH and the pH to determine the correct answer to question 3. Now, this falls under topic 8.1, Introduction to Acids and Bases. The pOH is equal to the negative log of the concentration of the hydroxide ion, and at 25 degrees Celsius, pH plus pOH is equal to 14. So the negative log of 0.025 is 1.60. So 1.60 is the pOH of this solution, and since pH plus pOH equals 14 at 25 degrees Celsius, then 14 minus pOH will give us the pH. 14 minus 1.6 is equal to 12.4. So the correct answer to question 3 is choice B. First, we calculated the number of moles of sodium hydroxide. Then we calculated the concentration of sodium hydroxide, which was the same as the concentration of the hydroxide ion. Then negative log the concentration of hydroxide, 14 minus pOH gave us the answer. So pH equals 12.4. Now let's take a look at question 4. In question 4, it says, the pH of solutions of two different monoprotic acids prepared at two different concentrations were measured and recorded in the table above. Which of the following statements correctly compares the relative strength of these acids and provides a valid justification? So if we can narrow down our choices A and B indicate that acid 1 is the stronger acid, and choices C and D indicate that acid 2 is the stronger acid. Let's go ahead and analyze the data that we are given in the table. So starting with this first row of the table, we can see that the concentration of each acid is listed as 5.0 times 10 to the negative 3 moles per liter. And the results indicate that the pH of acid 2 is lower than the pH of acid 1. Now, moving on to the next row of the table, we can see that the concentration of each acid is listed as 4.0 times 10 to the negative 4 moles per liter. And yet again, in terms of the pH of acid 2 is lower than the pH of acid 1. Now I'm going to show you some information from an earlier video for topic 8.3 that I did. So this particular question comes from that earlier video where I was discussing topic 8.3, weak acids and bases. Now here in this particular table, we can see that there's HNO3, so that's nitric acid, and then there's HNO2, that's nitrous acid. They have the same initial concentration of 0.036 moles per liter, but look at those pH values. So nitric acid, HNO3, is a stronger acid than nitrous acid, HNO2, and here's why. Comparing the concentration of the hydronium ion, we can see that nitric acid has a higher concentration of the hydronium ion, and then looking at the pH values, the nitric acid has a lower pH value, and when percent ionization was calculated from this information, we see that nitric acid had a higher percent ionization. So higher concentration of hydronium, lower pH, and higher percent ionization. Now, what about the Ka value? Well, here we can see the Ka, which is equal to the concentration of the hydronium ion times the concentration of A minus, or the conjugate base, divided by the concentration of that monoprotic acid. So if you compare two different monoprotic acids, such as HX and HY, and if they have the same initial concentration of the acid, then you can use the data to compare the relative strength of these two acids. The stronger acid should have a higher concentration of the hydronium ion, a lower pH value, a larger value for the percent ionization, and a larger Ka value. On this next slide, this was also from my video for topic 8.3, weak acids and bases. So as I was comparing three different acids that all had a concentration of 0.50 moles per liter, for the concentration of the acid, we discovered a general trend. The stronger acid is the acid that has the higher Ka value, and then comparing two different acids that have the same initial concentration, the stronger acid will have the lower pH value. So since the pH of acid 2 is lower than the pH of acid 1 for this particular set of data, then we can say with confidence that acid 2 is the stronger acid. Let's go ahead and eliminate choices A and B. Now, looking at choice C, it says that acid 2 is the stronger acid because it has a smaller Ka value, but that's not correct. It would be the larger Ka value that would be associated with the stronger acid. Now, that makes the correct answer to number 4, choice D. And what I'm going to do is go ahead and calculate the percent ionization for each of these acids based on the data. So starting with acid 1, I'm going to do the following calculation for acid 1. So the percent ionization is a ratio of concentration of the hydronium ion, which for acid 1 in this particular row of the table would be 10 to the minus pH, so 10 to the minus 3.52, divided by the initial concentration of the acid, which for this particular row of the table would be 5.0 times 10 to the negative 3 moles per liter, and then times 100. So acid 1, based on this math, has a percent ionization of 6%. Now let's repeat that calculation for acid 2. So it's going to be 10 to the minus pH, or 10 to the minus 2.30, that's the concentration of the hydronium ion, divided by the initial concentration of the acid, which is 5.0 times 10 to the negative 3, and then times 100. Now, instead of getting 6% ionized, which we got for acid 1, take a look at this particular value. It's 100% ionized. So again, this is just confirmation that the reason why D is the correct answer to question 4 is because acid 2 is the stronger acid, and it definitely has a larger percent ionization value. All right, well, hopefully that makes sense. That was question 4. Now let's take a look at question 5. In question 5, it says, the table above shows data for 3 different solutions of HC2H3O2, that is known as acetic acid or vinegar. 3 different solutions of acetic acid are listed at 25 degrees Celsius. Based on this data, which of the following is most likely to occur when a sample of acetic acid is diluted with water? And so diluted with water, as you can see in the table as you go from top to bottom, the concentration of the acetic acid in that first column is decreasing from top to bottom. So it's 1.0 times 10 to the negative 2 moles per liter, and then that decreases to 1.0 times 10 to the negative 3, and then finally 1.0 times 10 to the negative 4. So the concentration of acetic acid is decreasing from top to bottom. So does this have an effect on the value of Ka, or does this have an effect on the percent ionization of acetic acid? So I'll start with the Ka value, which is what we see in choices A and B. Now, back in Unit 7, when you were learning about the equilibrium constant, you learned that a change in temperature causes a change in the equilibrium constant K. So in this particular question, because there is no change in temperature, each of these solutions are at 25 degrees Celsius, the temperature remains constant, so the value of the equilibrium constant Ka for acetic acid will not be affected. So we can eliminate choices A and B. There's no change in temperature, so no change in the value of Ka. Now, let's take a closer look at the percent ionization. Just like we saw in question 4, percent ionization is a ratio, concentration of the hydronium ion, which is listed in this table, divided by the initial concentration of this weak acid, times 100. So I'll start with the first row of the table. It's going to be 4.2 times 10 to the negative 4 for the concentration of the hydronium ion, divided by 1.0 times 10 to the negative 2, and then times 100. Now that works out to be 4.2% ionization. Let's move on to the next two rows of the table and do a similar calculation. So concentration of the hydronium ion, 1.3 times 10 to the negative 4, divided by 1.0 times 10 to the negative 3 and times 100. So now we get 13% ionization. And then finally in the last row of the table, 3.4 times 10 to the negative 5, that's the concentration of the hydronium ion, divided by 1.0 times 10 to the negative 4, the initial concentration of the acid. And when we do that math, we get 34% for the ionization. Now, if this looks familiar, this was presented in my earlier video for topic 8.3. So what we're going to see is in this particular slide, there's a set of data for an acid, and the concentration of the acid is decreasing from top to bottom, but you can see that the percent ionization is increasing. So when a weak acid is diluted, the percent ionization of the acid increases. So the correct answer to number 5 is choice D, that when a sample of this acetic acid is diluted with water, we can see that the data shows us that the percent ionization of the acid actually increases. So number 5 is choice D. Now let's take a look at question 6. Question 6 begins by stating the following. The structural formula of maleic acid, which has the chemical formula H2C4H2O4, is shown at right. Now, maleic acid is a diprotic acid, and the two acid ionization processes that occur are represented by the following equations. So in the first equation, they start with maleic acid, H2C4H2O4. A proton, or an H plus ion, is transferred to water, and then that produces the hydronium ion, H3O plus, along with the conjugate base, HC4H2O4 minus. So that first ionization event is labeled as Ka1. The equilibrium constant for that reaction is Ka1. That's 1.5 times 10 to the negative 2. Now there's a second ionization process, and that happens when the conjugate base from the first equation loses another proton. So another proton, H plus, is transferred to water. So in that second equation, the HC4H2O4 minus ion loses another H plus ion, another proton is transferred, and now we get another hydronium ion, H3O plus. We also produce a conjugate base, which now has the chemical formula C4H2O4 2 minus. So two separate ionization equations, and that second equation also has a Ka value, but that's labeled as Ka2, 8.5 times 10 to the negative 7. Now we come to the question for question 6. Which of the following identifies the 4 species that are present in an aqueous solution of maleic acid, and we have to rank them from highest concentration to lowest concentration at equilibrium. So because maleic acid is a weak acid, this question falls under topic 8.3, weak acid and base equilibria. This highlighted essential knowledge statement summarizes the behavior of a weak acid. Weak acids react with water to produce hydronium ions. However, only a small percentage of molecules of a weak acid will ionize in this way. Thus, the concentration of the hydronium ion, H3O+, is much less than the initial concentration of the molecular acid. And the vast majority of the acid molecules remain unionized. So take a look at those Ka values. Because they are less than 1, that means that we are favoring the reactants on the left side of the equation and not the products on the right side. So because Ka1 and Ka2 are less than 1, we are favoring the reactant side. So I can conclude that the maleic acid on the left has a higher concentration than its conjugate base on the right. Well, if that's true, then we can eliminate choices C and D, so that the concentration of H2C4H2O4, which is maleic acid, is greater than the concentration of the conjugate base HC4H2O4-. Well, now that we've narrowed down the answer to question 6, it's either A or B, let's take a closer look at that second ionization event. If there were only one ionization event, then we could conclude that the concentration of the hydronium ion would be equal to the concentration of that conjugate base, HC4H2O4-. However, as we can see, there is a second ionization event, and that results in the formation of additional hydronium ions. So therefore, the concentration of the hydronium ion must be greater than the concentration of the HC4H2O4- ion. That makes choice B the correct answer based on that slight increase in the concentration of the hydronium ion relative to that conjugate base HC4H2O4-. So the correct answer to question 6 is choice B. Now let's take a look at question 7. In question 7, we are given a data table, and it says that the pKa or pKb values of some weak acids and bases are listed in the table above. And the question asks, which of the following solutions has the highest pH? So all 4 of the solutions that are listed in question 7 have the same concentration of 0.1 moles per liter. Let's consider pH and how we can rank these 4 substances. So in this table, I have a pH of 1, 4, 7, 10, and 13. Now I'm going to fill in this table with either the concentration of the hydronium ion, H3O+, or the concentration of the hydroxide ion, OH-. So I'll start with a pH of 7. So I have 10 to the minus 7 for the concentration of the hydronium ion and the hydroxide ion. And now I move to a pH of 4 and a pH of 1. So what's the general trend in this table? That as the pH decreases, the lower the pH is, the higher the concentration of the hydronium ion and the stronger the acid is. Now moving in the other direction toward a pH of 10 or 13, what we can see is that as the pH increases, a higher pH is associated with a higher concentration of hydroxide, and then that would be a stronger base. So in question 7, it says, which of the following solutions has the highest pH? So we are looking for a substance that behaves as a base, not a substance that behaves as an acid. Now, the first 2 substances that are listed in this table are HF, or hydrofluoric acid, and then HCN, or hydrocyanic acid, and pKa, that represents a substance that would behave as an acid. The next 2 substances, which have pKb values, are trimethylamine, CH3 parentheses 3N, and aniline, C6H5NH2. So those behave as weak bases. Since we're looking for a substance that has the highest pH, it's definitely going to be a base and not an acid. So we can narrow down our choices to either C or D. Now we have to ask the following question. Which of these 2 substances is the stronger base? Well, the higher the Kb value is, the stronger the base is. And we don't have Kb values given to us let's go ahead and calculate the Kb so we can answer question 7. As you can see on the equation sheet, the pKb is equal to the negative log of the Kb value. So if we already have the pKb, that would be 10 to the minus whatever that value is to determine the Kb. So 10 to the minus 4.19 gives us a Kb of 6.5 times 10 to the negative 5, and that's for trimethylamine. If we repeat that calculation for aniline, it would be 10 to the minus 9.42, and we get 3.8 times 10 to the negative 10. So the correct answer to question 7 is whichever substance is the stronger base, it's going to have the larger Kb value. So that would be trimethylamine, which has a larger Kb value of 6.5 times 10 to the negative 5. So the correct answer to question 7 is choice C. Now, let's take a look at question 8. In question 8, we are given a chemical equation, and it says that the ionization of hypobromous acid, which has the chemical formula HOBr, is represented above. So we can see in this chemical equation that the HOBr behaves as an acid. It is a proton donor, so it donates H plus to water. And then on the other side of the equation, we can see that it produces the hydronium ion, H3O plus, as well as the conjugate base, OBr minus. Now this is behaving as an acid. You can see that the equilibrium constant is labeled as Ka, and that is equal to 2.2 times 10 to the negative 9. So HOBr is classified as a weak acid. Now this question goes on to say that a certain solution of this hypobromous acid has a pH of 4.50. And the question is, what is the approximate concentration of the unionized HOBr in the solution? So I'm going to start by writing the generic Ka expression, which I can get from the AP Chemistry equation sheet. So Ka is equal to this ratio of the concentration of the hydronium ion times the concentration of the conjugate base, A minus, divided by the concentration of the weak acid, HA. Now I'm going to substitute HOBr for HA, and then OBr minus for A minus. So now this is the Ka that would correspond to this equation for question 8. And that is equal to 2.2 times 10 to the negative 9. Now, it does tell us that this particular solution has a pH of 4.50. And remember that if you know the pH, then the concentration of the hydronium ion is equal to 10 to the minus whatever that pH value happens to be. So in this case, it would be concentration of the hydronium ion is equal to 10 to the minus 4.50. And when I do that calculation, I get 3.16 times 10 to the negative 5 moles per liter. Now, that is not only the concentration of the hydronium ion in this solution, it is also equal to the concentration of the conjugate base, OBr minus, and that is simply because of the 1-to-1 ratio in terms of the equation. So for every 1 mole of the hydronium ion that is formed, you also get 1 mole of the conjugate base, OBr minus. Now I'm going to put those values, 3.16 times 10 to the negative 5, into the Ka expression. I'm going to set this equal to 2.2 times 10 to the negative 9. And now you can see from this setup that the only thing that we don't know in this expression is the concentration of HOBr. That's what we're trying to find in question 8. What is the approximate concentration of the unionized HOBr in the solution? So I'm now just going to rearrange this equation to get the concentration of HOBr on a side by itself. And when I do that manipulation, I can now simply plug in these numbers into my calculator. So 3.16 times 10 to the negative 5 which is squared on the top, and then divided by 2.2 times 10 to the negative 9. And so when I do that math, I get 0.45 moles per liter for the concentration of HOBr. So that is the correct answer to question 8. Question 8 is choice C, 0.45 moles per liter. Now let's take a look at question 9. In question 9, it says samples of solid KNO2, which is known as potassium nitrite, and solid NH4NO3, which is known as ammonium nitrate, are dissolved in separate beakers that each contain 100 milliliters of water. One of the salts produces a slightly basic solution. Which of the following equations best represents the formation of the slightly basic solution? So I'll start with choices A and B. And you can see on the right side of those equations in choices A and B that we can see H3O+, which is known as the hydronium ion. Now in choices A and B, the equation shows a reaction that leads to the formation of hydronium ions, but this would cause the solution to become slightly acidic, not slightly basic. So an increase or the production of the hydronium ion would cause an acid solution, not a basic solution. So we can eliminate choices A and B. Now, looking at choices C and D, they both involve the formation of the hydroxide ion, so they would represent the formation of a slightly basic solution, but there's a slight difference between choices C and D. In choice C, we have NO2- reacting with water, and in choice D, we have NO3- reacting with water. So we have the nitrite ion, NO2-, versus the nitrate ion, NO3-. Now, let's take a look at topic 8.2, pH and pOH of strong acids and bases. Now, there are 6 strong acids that AP Chemistry students should know to prepare for the AP Chemistry exam. And that includes HCl, HBr, HI, and then 3 others. But one of them is listed as HNO3, that's nitric acid. HNO3 is an example of a strong acid. It is 100% ionized in aqueous solution. So now take a look at choice D of question 9. In choice D, it shows the nitrate ion, NO3-, reacting with water to produce the molecular version of HNO3, which is classified as a strong acid. So it is very unlikely that the NO3- ion, or the nitrate ion, would react with water to form molecules of a strong acid such as HNO3. Since HNO3 is a strong acid, it would be completely broken up in water and would not exist in that molecular form, HNO3. So by eliminating choice D, that does make C the best answer to question 9. I'm going to explain this a little bit in more detail by reminding you of something that I had taught in an earlier video for topic 8.3. So what you can see on this slide are 2 important categories of weak bases. On the left, we see molecules that are known as amines. They all contain nitrogen atoms, and that lone pair of electrons on the nitrogen atom acts as a proton acceptor, so that would behave as a base. And then on the right side of this slide, you can see anions, or negative ions, that represent the conjugate base of a weak acid. So the acetate ion, the hypochlorite ion, the hydrogen carbonate ion, as well as the nitrite ion, NO2-, are examples of negative ions that are derived as the conjugate base of a weak acid. And so therefore, if you are a weak acid, then the conjugate base behaves as a weak base. So here's another way to clarify why choice C is the correct answer for question 9. Since nitrous acid, which is HNO2, is not on the list of 6 strong acids, nitrous acid, HNO2, is classified as a weak acid, and therefore its conjugate base, NO2-, is classified as a weak base. So that makes choice C an acceptable equation, indicating the formation of a slightly basic solution. On the other hand, since nitric acid, HNO3, is classified as a strong acid, then the NO3- ion, or the nitrate ion, would be classified as neutral and has no effect on the pH of a solution. So that nitrate ion is not likely to combine with water to form the molecular version of something that we know is a strong acid. It is 100% ionized in aqueous solution. Again, the correct answer for question 9 is choice C. Now, let's take a look at question 10. Question 10 says the following. Caffeine, which has the chemical formula C8H10N4O2, is a weak base with a Kb value of 4.3 times 10 to the negative 10. And the pH of a 0.01 molar solution of caffeine is closest to, and then we can see 4 numerical choices. So to start off this problem, I'm going to write the Kb expression from the AP Chemistry equations and constant sheet. So in this Kb expression, in the denominator, we can see that the letter B is in brackets. That represents the concentration of the weak base. And in the numerator of this expression, we can see the concentration of the hydroxide ion, OH-, as well as the concentration of the conjugate acid of that weak base, which is written as Hb+. So when the weak base, represented by the letter B, reacts with water, it produces the conjugate acid Hb+, along with the hydroxide ion. Now, we know that the chemical formula of caffeine is C8H10N4O2. So I'm going to replace the letter B on the left side of the equation with the formula of caffeine, and then on the right side of the equation, I'm going to replace Hb+ with the conjugate acid of caffeine. So it looks like this. So we have caffeine reacting with water to produce its conjugate acid, as well as the hydroxide ion. Now I'm going to write the Kb expression for this particular equation. So I can see that there's the chemical equation for the reaction of the weak base, caffeine, with water, and now here is the Kb expression for that particular reaction. And that is equal to, as we are given in this problem, 4.3 times 10 to the negative 10 represents the value of Kb. Now that 0.01 molar solution, that would be the concentration of caffeine, and that would go in the denominator of this expression. In the numerator, those are unknown quantities, but they are the same based on the 1-to-1 mole ratio in terms of the coefficients. So therefore, I have X and X as the unknown quantities in the numerator. Now, technically, in the denominator would actually be 0.01 minus X. But you may recall, if you watched my video for topic 8.3, when I was talking about weak acids, and this also applies to weak bases, that on the AP Chemistry exam, you will not need to use the quadratic equation to solve any mathematical calculations. So whether it's a weak acid or a weak base, that minus X that represents the dissociation or the ionization of that particular weak acid or that weak base, that minus X is small enough that it can be ignored. And that simplifying assumption allows you to complete the problem without using the quadratic formula or the quadratic equation. Now, back to this particular question. So we have the Kb, which is 4.3 times 10 to the negative 10. We have the concentration of caffeine in the denominator, which is 0.01. And in the numerator, we have two unknown but equal quantities represented as X and X. So X squared is equal to 4.3 times 10 to the negative 10 times 0.01, and that equals 4.3 times 10 to the negative 12. So if that equals x squared, I'll take the square root of that number, and the square root of 4.3 times 10 to the negative 12 represents the value of x, which is the concentration of the hydroxide ion in this 0.01 molar solution of caffeine, the weak base. So when I take that square root, I get 2.1 times 10 to the negative 6 moles per liter. That is the concentration of the hydroxide ion. Now, to get the answer to question 10, I still need to do two things to that number. 2.1 times 10 to the negative 6 is the concentration of the hydroxide ion. And those two things are, first, take the negative log of that number, and that will give me the pOH value. So when I do the negative log of 2.1 times 10 to the negative 6, that is equal to 5.68. But again, choice A, 5.7, is not the correct answer to question 10. So what I have right now is the pOH. I need to get the pH, which means I'm going to do 14 minus the pOH value. So pH plus pOH equals 14. 14 minus pOH equals pH, and 14 minus 5.68 is 8.32. So the correct answer to question 10, what is the pH of a 0.01 molar solution of caffeine? The answer is 8.3. So hopefully that makes sense. The answer to question 10 is choice B, 8.3. Now let's take a look at question 11. In question 11, we are given an example of a weak acid. It says propanoic acid, which has the chemical formula HC3H5O2, is a weak acid that ionizes in water according to the equation above. So we can see propanoic acid, it loses a proton or H plus ion, which is transferred to the water, and that produces the hydronium ion and the conjugate base, which would be C3H5O2-. So we are given the equation for the ionization of that weak acid, and then we are also given the Ka value of 1.3 times 10 to the negative 5. Now the question says, which of the following provides the best estimate of the pH of a 5 times 10 to the negative 3 molar solution of this propanoic acid, and identifies the species at the highest concentration, excluding water, in the solution. So for the species at the highest concentration, our choices are either the propanoic acid formula, HC3H5O2, or the hydronium ion. Now remember, in topic 8.3, weak acids and bases, or weak acid and base equilibria, that first essential knowledge statement describes the behavior of a weak acid. It says weak acids react with water to produce hydronium ions. However, only a small percentage of molecules of a weak acid will ionize in this way. Thus, the concentration of the hydronium ion is much less than the initial concentration of the molecular acid, and the vast majority of the acid molecules remain unionized. So in this solution, and you can see that the Ka is less than 1, it's 1.3 times 10 to the negative 5, we are favoring the reactants. On the left side of the equation, we are not favoring the products on the right side of the equation. So there should be a higher concentration of the molecular acid in solution and a lower concentration of the hydronium ion. So it's only partially ionized in aqueous solution. So since the HC3H5O2 would be a species at a higher concentration, then we can eliminate choices A and C, which indicate that the hydronium ion has a higher concentration. So correct answer is either B or D. Now let's see if we can calculate the pH of a 5 times 10 to the negative 3 molar solution of this weak acid, the propanoic acid. So I'm going to write the Ka expression based on this equation. That would be concentration of the hydronium ion times the concentration of the conjugate base C3H5O2- divided by the concentration of the propanoic acid, and that is equal to the Ka, which is 1.3 times 10 to the negative 5. So we know in this problem that we have a solution with a concentration of 5 times 10 to the negative 3 moles per liter. So that concentration goes in the denominator of this expression. And in the numerator, we have two unknown quantities, but they are equal to each other based on the 1-to-1 mole ratio in the coefficients. So that would be X and X. And I've already mentioned how we use that simplifying assumption that the minus X that might appear in the denominator of this expression, that X is small enough that we can ignore it, make that simplifying assumption to make our math easier. Let's go ahead and solve for X, and X represents the concentration of the hydronium ion in this 5 times 10 to the negative 3 molar solution of this weak acid. So X squared is equal to 1.3 times 10 to the negative 5 times 5 times 10 to the negative 3. So X squared is equal to 6.5 times 10 to the negative 8. I'm now going to take the square root of that number, and the square root of 6.5 times 10 to the negative 8 represents the value of X as well as the concentration of the hydronium ion. So when I did the square root of 6.5 times 10 to the negative 8, I got 2.5 times 10 to the negative 4. If I take the negative log of this number, I will get the pH. So the negative log of 2.5 times 10 to the negative 4 gives me a value of 3.6. So the correct answer to question 11 is that this solution has a pH of 3.6, and the molecular acid on the left side of the equation, the C3H5O2 molecule, would have a higher concentration than the hydronium ion. So correct answer to number 11 is choice D. Now let's take a look at the last question in this packet. This is question 12. In question 12, we are given a chemical equation for a substance which is known as the hypochlorite ion, has the formula OCl-, that reacts with water as a weak base. So we know that this substance, OCl-, is behaving as a weak base. It is not a proton donor like we saw in question 11. This is a proton acceptor. So it accepts H+ from water, and then it produces its conjugate acid, which has the chemical formula HOCl, and it also produces the hydroxide ion. So this substance is behaving as a weak base. We are given the symbol Kb on the right side of that equation, but then it says equals question mark. So our goal in question 12 is to actually calculate the value of Kb. Let's see what else we know about this particular solution. It says a solution of 0.025 molar sodium hypochlorite, which is NaOCl, has a pH of 9.96. So on the basis of that information, which of the following is the best estimate of the value of the equilibrium constant Kb for the reaction shown above at 25 degrees Celsius? So let's see if we can plug in numerical values into both the numerator and denominator of the Kb expression and then solve for the value of Kb. So here's our Kb expression. We have concentration of the HOCl, which is the conjugate acid of the hypochlorite ion. We also have concentration of the hydroxide ion. And then in the denominator, we have the concentration of this hypochlorite ion, OCl-. Now we are told that we have a solution of 0.025 molar sodium hypochlorite. So that means that there is a concentration of the hypochlorite ion that is equal to 0.025 molar. So that number goes in the denominator of the Kb expression. Now, let's see if we can fill in numbers in the numerator of this Kb expression. We are given that this solution has a pH of 9.96. So how can we turn a pH of 9.96 into the concentration of the hydroxide ion? So our first step is to convert from pH into pOH. And the relationship between pH and pOH is the following. pH plus pOH equals 14 at 25 degrees Celsius. Therefore, pOH equals 14 minus pH. So 14 minus 9.96 is equal to 4.04. Now that we know the pOH is equal to 4.04, then the concentration of the hydroxide ion is equal to 10 to the minus whatever this pOH value is. So that would be 10 to the minus 4.04. So the concentration of the hydroxide ion is equal to 10 to the minus 4.04, and when you do that calculation, you get 9.1 times 10 to the negative 5. Now, based on the 1-to-1 mole ratio of the coefficients on the right side of that equation, the concentration of the hydroxide ion is equal to the concentration of HOCl. So for every 1 mole of HOCl that is formed in this equation, you also get 1 mole of the hydroxide ion. So those two numbers are equal. Again, they're not x and x. We're not solving for x. We know what those values are because we were given the pH, so we could do that calculation. So now you can see I can fill in the Kb expression with 9.1 times 10 to the negative 5, and that number is going to be squared in the numerator of this expression, and then divided by 0.025. So when I do that particular calculation, the number I get is 3.3 times 10 to the negative 7. So that is the value of Kb, which means that the correct answer to question 12 is choice B. We put the concentration of the sodium hypochlorite, which is the concentration of the hypochlorite ion, 0.025, in the denominator. We converted pH into pOH, and then we calculated the concentration of the hydroxide ion, and then that number was put in the numerator, and it was equivalent to the concentration of HOCl. So we had that particular number squared divided by 0.025. Now, one more slight change, perhaps, to my numerical answer. Take a look on this next slide. You will notice in some problems I had mentioned we can make that simplifying assumption that the minus x portion in the denominator of the Ka or the Kb can be ignored to make the math easier. But in this example, I know what the value is. So I went ahead and did the math to prove to you that there really was not a significant change in the value of my denominator. So 0.025 minus the 9.1 times 10 to the negative 5, which is now a known value, I got 0.0249 in my denominator. This just proves the point that that minus x portion was relatively small compared to the concentration of this weak base, so that could be ignored when I'm solving for x, but you can see it did not significantly change the answer. So 0.0249 is very close to 0.025. Okay, well, hopefully you can see how we calculated the value of Kb for question 12. Question 12 is the last question in the packet, therefore this is the end of the video. I hope that you found all of these answers and explanations helpful. Thanks for watching.